Hello, everyone. The project I'm going to be going over is the Woodward Patternation Stand. So for this project, we were responsible for fabricating a production test machine to test the spray pattern of aerospace fuel nozzles and measure the distribution of their spray and make sure it is to the customer's specifications. Some of our key specs here were fuel measurement, nozzle and spray bar actuation vertically and rotationally, pressure transducer integration, and LabVIEW integration. This is the machine. The upper part here is where the spray bars or fuel nozzles will be, actuate up and down and rotate, and then down below is where things are collected and measured. The machine frame was constructed of 80/20 aluminum extrusion. This makes it easy to add stuff on later and mount things. Polycarbonate or plexiglass panels were used for fuel containment, and we will be hooking up to Woodward's fume exhaust to evacuate fumes from the top section. Sheet metal plates are used to isolate different areas of the machine, and fuel will be pumped out by Woodward's flow stand. For vertical actuation, we have a single servo motor, and this servo motor is driving two lead screws via a chain and sprocket system. And this system has an idler over on the far end to make sure we're not blocking the center area, and some tensioner on it as well. This is also guided by a 3/4 inch linear shaft and a ball bearing. For rotation, we used a 1/2 inch plate and a slew gear. That was the main part of the rotation, was the slew gear. This gear fixes in the middle and the outer portion rotates. So we bolted another plate to the outer portion, and this allowed us to rotate the spray bar. This is rotated with the same servo motor, but this time it has a gear ratio of about 10/1, and this servo, similar to the last one, is homed with hard stops. For fuel collection and transfer, we are using Woodward's existing fuel collection arrays shown on the left side of the screen. We have 48 transfer hoses available to be hooked up, and bulkhead fittings like the one shown below are used to allow fuel to pass through the hoses through different plates. For fuel measurement and evacuation, fuel is collected in 48 tubes and measured in each of these tubes. The pressure transducers will hook up to these tubes. There's a hard line going from these small fittings down on the right called transducer hose hookups. Those are going there, and using the density of the test fuel, we're able to measure the height or volume of fuel in each location. And this allows us to determine the pattern or distribution of the spray. And at the end of each cycle, some pneumatic valves on the left are actuated, and this allows fuel to dump out of the fuel evacuation connections. For fuel flow, fuel is sprayed from the top. It's collected in a collection array, goes through some hoses, through bulkhead fittings that allow it to go through the plate, through more hoses down into the solid steel tubes, and here the fuel level is measured with the pressure transducers. And at the end of each cycle, fuel is evacuated, similar to how it was shown in the last slide. For electrical power, we have a 120 AC volt power supply or power source that can supply up to 20 amps. The devices we're using are surge protectors, 24 and 75 DC volt power supplies. For protection, we have a 20 amp fuse on the main power line, 12 amp on the 75 volt power supply, and 10 amp on the 24 volt power supply. And as you can see below in this table, the maximum power draw in the worst case scenario on this machine is far below the rated power that these power supplies are able to output. For the safety system, we had to make sure the machine is safe when the e-stop is pressed. Safety from Woodward's flow stand and the power and our patternator will need to interact. To achieve these things, we're using a banner safety controller, a dual channel e-stop push button, and a manual safety reset button. The single channel e-stop push button is the main component here, and the banner safety controller allows us to use simple logic gates to control outputs to the main relays for this machine. Pressure transducers were used, as mentioned earlier, to measure the amount of fuel in each array. There are 16 connections on each of these scanny valve pressure transducers, so we needed 3 of them and 2 communication cables. These cables are used to daisy chain from one scanny valve to the next, or scanny valve synchronous Ethernet protocol, which is similar to this, just daisy chaining them. And the primary scanny valve will connect directly back to the CDAQ via Ethernet. For the control system, the sponsor selected a CDAQ module, and the sponsor will be programming this machine. The components here are listed below, and the output modules here send commands directly to the motors and receive inputs back, letting us know where the motors are at any given time on this machine. So for the pneumatic system, Woodward was providing from anywhere from 120 to 100 psi of shop air, and the patternator will use a regulator to regulate the air pressure down to 90 psi. Here we're using fairly standard components: a valve stack, main shutoff valve, fuel regulator, pressure regulator, sorry, three 16-port manifolds, and 48 cartridge valves, which are used to allow the fuel to evacuate at the end of each cycle. Some major obstacles here were integrating a vertical actuation system without interfering with Woodward's phase Doppler particle analyzer testing. This is a test Woodward performs, and we needed to leave about 12 inches of space from the bottom of the nozzles to the top of the machine. It was also difficult to size assembly components and get them working together. We also had some long lead times on custom parts, and integrating the LABVIEW CDAQ also proved to be difficult. But overall, the project went fairly well, and all the team members are happy with where it is today and excited to get it handed off to the sponsor and everything finished up. Thank you for your time, and I hope this video provided you with some useful information.